CyberMech, a novel runtime substrate for cybermechanical systems. The CyberMech software platform is a collaborative, interdisciplinary project in computer science and civil engineering. Our goal is to co-develop the theory and practice of cyber-physical system design in the specific application of real-time hybrid simulation, or RTHS. Cyber-physical systems are a common feature of modern life. Anytime a computer interacts with some physical process, the combination of computer hardware, sensors, and actuators can be said to be a cyber-physical system. Cyber-physical systems can be anything from the anti-lock braking system in your car to large, geographically distributed systems like the power grid. All these systems have one thing in common: software that controls how the system operates. The goal of the CyberMech project is to understand this software through a specific cyber-physical application called real-time hybrid simulation. Hybrid simulation is the answer to a major problem in structural and civil engineering. New structural designs must be tested and validated before being used, but this can be very expensive. For example, suppose you have a new idea for mitigating earthquake damage. A full-scale empirical test would involve building a real structure with your idea and subjecting it to earthquake conditions. This is very expensive and difficult for small structures and impossible for large structures like bridges and skyscrapers. An alternative to a full-scale empirical test is the use of a computer simulation. A simulation is much cheaper and faster than an empirical test, but is not always applicable. If your idea is so new that it has never been tried before, there might not be a good way to simulate it. If your idea is very complex, a computer simulation might not be good enough to convince others that your idea works and is safe. Hybrid simulation is a solution that allows us to combine physical experimentation alongside computer simulation. Rather than building an entire structure just to test one new idea, we can build the one new idea and simulate the rest of the structure. Suppose we have a new idea we want to try in a 3-story building. We want to do something special to the first floor deck, but the rest of the structure is done using existing techniques. As a result, we know how most of the structure behaves, but we do not know how that special first floor is going to act. Because of this, we can't simulate the entire structure, and doing a full-scale test is expensive. This is a great situation to apply hybrid simulation. In our hybrid simulation, we simulate parts of the structure where we are able. In this example, we cannot simulate the first floor deck, so we construct a physical replica. This physical specimen is then connected to a set of actuators and sensors that allow the virtual structure and the physical specimen to interact. Taken together, the composite cyber-physical structure can faithfully represent the building as a whole, even though some parts only exist as a computer simulation. This lets us test our new design for a fraction of the cost of building the entire structure. At test time, we can use historical records to simulate an earthquake on that virtual part of our test. The computer simulation then computes the forces that should be applied to the physical specimen and uses actuators to do so. A set of sensors records how the physical specimen responds and feeds that data back into the computer simulation. In order to get good experimental accuracy, we want a computer system that is fast and reliable. For hybrid simulation, there are 2 basic steps: a numerical simulation step and a sensing and actuation step. The ability to send actuator commands at regular intervals allows us to have predictable physical performance, while the ability to compute the numerical simulation quickly allows us to perform the whole sensing and actuation loop faster. For this application, it is important to be both predictable and fast. The general goal is to perform this loop 1,000 times per second, or once every millisecond. Real-time hybrid simulation is the specific focus of the CyberMech project. As a software platform, CyberMech allows us to couple parallel computation with real-time semantics, which allows for larger and more accurate experiments. In the realm of experimental design, our work on experiment stability and control allow us to be confident about the physical performance of our RTHS experiments. The remainder of this video is a demo of RTHS in action, followed by several interesting experimental results from the last year. In this demonstration, we have a simple two-story composite structure. The ground floor is numerically simulated as a virtual structure, and a scale model attached to an electric shake table represents the first floor. For this test, historical earthquake ground motion is used to drive the composite structure. When the virtual structure is excited, the ground underneath the composite structure is moving. This will induce a movement in the first floor deck translated through the ground floor support columns. The first floor is a scale model, so we must physically reproduce this motion. We use a sliding table called a shake table to produce this movement. This is a video of an RTHS test. On the left, you can see our shake table with an attached physical specimen. As was just described, this is actually one half of a composite cyber-physical structure. This demo is being run with a commercially available piece of software called Simulink because of its superior graphical display. Simulink lacks support for parallel computation, which has been a major focus of the CyberMech project. For this simple test, parallel computation is not required. As the table is moving, two lines are displayed on the graph. The blue line represents the location of the first floor deck that serves as the interface between the virtual structure and the physical specimen. The orange line represents the voltage command that is sent to the motor in order to achieve the desired displacement. As said previously, one focus of our project has been to do parallel computation in real time. To generate this graph, we simulated a realistic 9-story structure. With sequential computation, we were only able to achieve a sensing and actuation rate of 660 times per second. With parallelism, we increased that to 3,000 times per second. This graph shows a simulated experimental error at the 9th story relative to a reference solution. The much higher periodic rate of the parallel implementation is able to achieve roughly an order of magnitude reduction in error relative to the sequential version. This graph shows the computational performance of the same 9-story simulation from before. Along the bottom of the graph, you can see that we vary the number of computer processors participating in the parallel computation. As we increase the number of processors, the periodic rate increases, as seen with the red line on the right-hand axis, and the running time of each periodic iteration decreases, as seen with the box plots on the left-hand axis. One interesting result is that the overall variability of timings did not increase as a result of parallel computation, which means that our parallel runtime is suitable for use in real-time systems. Anticipated RTHS requires full parallel operation alongside meaningful physical experimentation. A milestone towards this objective is a full simulation of RTHS, called virtual RTHS. This diagram depicts one such VRTHS, where the anticipated physical substructure is an MR damper connected to a hydraulic actuator. The anticipated numerical substructure is a 9-story structure subjected to earthquake loading. The VRTHS is partitioned so that the physical substructure is simulated on a separate machine from the numerical structure, and these machines communicate via analog signals. This allows the entire RTHS system to execute as though it would during a real experiment. It should be possible to completely substitute the actual physical apparatus for the virtualized physical components with some fine-tuning. Here we see parallelism's effect on computation during full-scale VRTHS. The 9-story numerical structure was iteratively refined to vary the computational requirement, which provides a range of computational difficulties while maintaining the physical semantics of the simulation. It can be seen that CyberMech's parallelization is effective in the context of this full VRTHS. Our project has also investigated multi-rate simulation, also called multi-time step simulation, which can be used when an RTHS virtual structure cannot be simulated in real time. In a multi-rate simulation, different aspects of the virtual structure are simulated at different timescales in order to make the most effective use of our computer platform. For example, here is a model of a bar with a notch in it. You can see that the mesh decreases in size around the notch, which better captures the behavior at that point. This is a good step towards optimizing computer resources, but a traditional computer simulation will still simulate the entire bar at once, even if there is nothing interesting going on at the ends, so to speak. A multi-rate approach allows us to simulate the noteworthy area around the notch at a finer time scale and thus more accurately than the rest of the bar. To do multi-time stepping formally, we split the problem into subdomains. In this example, subdomain A is solved at a large time step, and subdomain B is solved at a small time step. Coupling terms along the internal boundary C maintain consistency between the two subdomains and conserve energy in the simulation. The two timelines show the layout of the multi-time stepping method. Subdomain A is advanced through the large time step delta capital T, and subdomain B is advanced through the small time step delta lowercase t. Once they have reached the same point in time, the two solutions are reconciled with each other with the coupling terms C. Using this method, we are able to accurately solve both subdomain A and subdomain B at appropriate time steps without using the additional computational resources to solve subdomain A at every small time step. In this example, the fast subdomain B is solved 4 times for every solution of the slow subdomain A, meaning that there is a time-stepping ratio of 4. The CyberMech platform naturally supports the execution of multiple simulations simultaneously. Given the multi-time stepping theory, we are left with the problem of how to choose each subdomain, as well as how to choose the time-step ratio between subdomains. We have developed a heuristic method to find suitably good subdomain decompositions for a given RTHS problem. Here we have 2 simulations, a truss on the left and a frame on the right. Both structures have a hypothetical load on their top left corners, at the red arrow. Our heuristic method finds subdomain decompositions that minimize simulation error across the entire structure. Here we have found a fast subdomain in blue and a slow subdomain in red. Notice that the fast subdomains are centered around the point of hypothetical loading at the top left of the structures. Such decompositions depend on the model being simulated, loading conditions, material properties, and computational capacity. We have developed a method for selecting an optimal decomposition into 2 subdomains. Here we show a slightly different application of multi-time stepping theory. Recall that the 9-story simulation from before did not run fast enough on a single processor. In this approach, we introduce a second, simplified model that does not capture the full structural dynamics, but is quick to compute. The fast model allows the system to perform frequent sensing and actuation, while the slow model maintains accuracy over large timescales. In this experiment, these 2 models run on separate computers. This distributed approach introduces particular problems due to delay between components of the system. We have developed a framework for analyzing the performance of such systems. In this graph, the red line is a reference solution that is computed from a highly accurate model that cannot be run in real time. Using the multi-rate approach, shown as a dashed black line, we are able to achieve real-time performance that is very close to this reference. The blue line shows the same RTHS without the multi-rate approach, which limited the sensing and actuation rate and resulted in a less accurate test. When performing an RTHS experiment, we must couple a physical structure with a computer simulation. Sometimes, these components interact in unexpected ways. When this occurs, the composite structure can become unstable, meaning that the physical specimen and the computer simulation are unsynchronized. The result is an invalid experiment and potentially dangerous physical behavior. This graph shows the execution of an RTHS experiment that has become unstable. As time progresses to the right, the physical displacement of the sliding table continues to increase without bound. This is a safety concern, as it will lead to wild oscillations capable of damaging equipment or hurting people. Our group has developed theoretical stability and performance indicators that allow us to analyze an RTHS experiment in the design stage. These indicators take into account certain characteristics of the physical and computational components and identify safe operating regions. Using these indicators, we can design experiments that work reliably and understand why other experiments fail. These graphs depict regions of stability bounded by curves that relate to physical parameters of the system. Using these indicators, we are able to perform RTHS experiments that were previously unstable. We have refined our measures of variability between individual executions of the same experiment. This is necessary to capture the degree to which we are able to succeed in reproducing the same experiment across different softwares or laboratories. Here you can see the relative evaluation of an RTHS experiment across two different software platforms, CyberMech and XPC, against a reference solution. While neither system reproduces the reference perfectly, the degree to which they are similar is able to be quantified, which is enough to draw meaningful conclusions. This slide shows the results of constraining the total allowed displacement of a virtual hydraulic actuator versus a control algorithm's desired output. One of our goals is to create a system for robust RTHS that allows practitioners to rapidly deploy and modify RTHS experiments. To enable this, we want the CyberMech platform to support the creation and enforcement of contracts that specify the behavior of physical systems under control. For example, an experiment may need to terminate because of hazardous conditions, such as nearing an actuator's safe operating limit. The specification of such constraints should be simple and descriptive, and enforcement should be automatic. Reliable platform support for such contracts will allow users to freely and safely conduct experiments. To facilitate the testing of such a system, we have simulated a broken encoder. Encoders are widely used to measure angular and linear displacements in mechanical systems. We use it to measure the linear displacement of our shake table. Damage to this sensor may cause a system to believe it is stationary when it is moving, or distort the reported movement. This graph shows the effect of simulating this hardware as damaged. On this graph, the region between the blue lines are considered broken, so that the system does not register change when the actual table is in that range. The red line is the actual location of the table. The green line is the location as reported by our simulated broken encoder. Notice the reported green value is constant while the red value is between the two blue bars. Since the encoder is not actually broken, this arrangement allows us to simulate broken hardware while maintaining safety at all times. This work was conducted at Washington University in St. Louis, Missouri, and at Purdue University in West Lafayette, Indiana. Thank you for your time.